Okay, so basically, if you look at first, we have the amino acid. Then we join two amino acids together by the peptide bonds to form the dipeptides, and we do have many amino acids join all of them together, maybe thousands of them amino acids. So you form the polypeptides, and we do know that polypeptide is a macromolecule. So why polypeptide we can claim is a macromolecule? Still remember a quick revisions here when we talk about macromolecule. For any macromolecules, they need to fulfill the 4 criteria, right? So first, they must have the repeating monomer. So in this case, the repeating monomer is amino acid. Okay, number 2, this repeating monomer must be either identical or similar. So in the context of polypeptides, they are similar, not identical, yeah, because all amino acids, we have 20 types of them. So if 20 types of them, you cannot actually say that they are identical. Okay, so just now we have drawn, okay, in the previous parts, when we want to form a dipeptide, we join the amino acid actually side by side, correct or not? Okay, or end to end, and by the process of condensation process. Okay, because of H2O is removed. Okay, so therefore polypeptide qualifies as the macromolecules. Okay, so the process to join all or link all amino acids together is by condensation process. So a complete proteins, it can be either one polypeptide chain only. So sometimes up to one polypeptide chain, they already can functions already. So no problem, a complete protein. But sometimes they might need more than one polypeptide chain to join together. Okay, and we want to break down the polypeptides. Definitely, we use the hydrolysis process by using the proteases. Okay, so if we want to study a polypeptide, even though we call it as a level organization or protein, but we actually referring to the polypeptides. So if you want to study a polypeptide, you can analyze them at 4 different levels. So which are 4 different levels? So we're going to look at them at the primary, secondary, tertiary, and quaternary structure. And each level will have their own checklist. Means that if I want to analyze particular thing, we were going to analyze it only these few items. We won't actually go beyond these items when we want to study. Okay, for example, if you look at this diagram, then we're going to look at this how we study our protein. So this is our protein. Can you see that? So this protein actually consists of 1, 2, 3, 4 polypeptide chains. Are you clear? So then we are going to zoom in into one polypeptide chain, and then we unfold it into non-folding structure. Can you see that? So now, if you make it something like linear, make them not folded, then if you look at this, okay, this amino acid number 1, or this is amino acid number 2, or this is leucine, this is alanine, for example. If you study the types of amino acid and their sequence, are you clear? Because we do know that amino acid A, B, C not the same as B, C, A. Are you clear? So in this context, when you study the type of amino acid and the sequence of the amino acid that form this polypeptide, okay, then this we study them at the primary structure. So the primary structure actually, when you study or analyze a polypeptide at primary structure, then we only look at the types of amino acid as well as their sequence. That's all, full stop. And this amino acid definitely have to be linked together by the peptide bonds. Okay, so primary structure. When we look at secondary structure, then we're going to look at how these polypeptides start to fold, okay, or coil. So they either coil into this what we call the alpha helix, helical structure, but we name them as alpha helix, or they fold. Can you see that they fold? Can you see that they fold like this? So they fold into this what we call as the beta pleated sheet. It's formed like something like a paper. Can you see that? A strip. Okay, try to imagine you cut the paper into the strip and then you place them side by side. Okay, one strip, second strip, third strip, something like this. Can you see that? So the rest of the amino acid, they form like the fold like this. So this one is called as the beta pleated sheets. So if you look at the formation, how many beta pleated sheets, how this alpha helix is formed, then we study them at the secondary structure. So secondary structure, we look at the polypeptide backbone, how they coil into the alpha helix, how they fold into the beta pleated sheets. This is the criteria or elements that we study at secondary structure. Okay, and if we go to the tertiary structure, then we look at how these polypeptides fold into the precise three-dimensional shape. So we use the word precise basically means that if there's no change in the primary structure of the polypeptide, no matter how you fold them, they will be the same. Today you fold them, tomorrow you fold them, the next year you fold them, it will be the same shape. So we call them as a precise three-dimensional shape. And how this shape can be maintained. Can you see that? When you fold into a precise three-dimensional shape and how this shape can be maintained, then actually we learn them or we study them or we analyze them at the tertiary structure. Can you see that? Level by level. And when you come to the quaternary structure, basically we study how these more than one polypeptide actually can join together. We can have 10 of them join together. We have 5 of them join together. We have 3 of them join together. As long as they are more than one joined together or linked together by the interactions of the R groups, then this one we call them as the quaternary structures. Are you clear? So not all protein will end up as a quaternary structure, because some protein up to tertiary structure, they will be able to function already. So in this case, okay, for example, our hemoglobin's molecule. Hemoglobin molecule actually have 4 polypeptide, okay? Hemoglobin molecule, they have 4 polypeptide chains joined together. So it means that we can analyze hemoglobin molecule up to the quaternary structure. Some enzyme, they only up to the tertiary, so means that they only have 1 polypeptide, so means that we analyze them up to the tertiary structure only. Okay, so what we're going to look at it now, we're going to analyze one by one, okay, in detail. Okay, we're going to start with the primary structure now. So in primary structure, what we're going to look at it here is we're going to look at the types of the amino acid that form that particular polypeptides, as well as their specific sequence of amino acid. And this amino acid, they are joined by the peptide bonds. So conventionally, which one is the first amino acid? I say that first amino acid, always remember, they must start with NH2. Okay, conventionally, we always put the NH2 as the beginnings of the polypeptide. Even when we draw the dipeptide, left-hand side always, okay, amino group first, and with the carboxylic acid. So this amino group is termed as amino terminal and or called N terminals, and end with the carboxyl terminal, which is the C terminals. So it means that all polypeptides, how we label them. Okay, let's say I have this polypeptide. Okay, so how we know which one is the first amino acid? We look at the N. If this N start with COOH and this N end with NH2, then how we label them? We label this as amino acid number 1, then 2, 3, 4, 5, 6, 7, 8. This is amino acid number 8 because amino acid number 1 always start with the N terminus. Are you clear? It's just a name we give to it to differentiate which one is the first one, which one is the last one. Why we need to do this? Because they are the amino acids, or we call them these are monomer. They are not the monomer. Okay, they are not identical. So in terms of glycogen, we don't do this. In terms of the starch, amylose, cellulose, we don't do this. We don't give the name or the label to the ends, and we don't give, okay, this is glucose number 1, this is glucose number 2. No need, because they are identical. But for protein or polypeptide, because each amino acid, they are unique, so therefore we need to label them. Which one is the first one? Which one is the last one? So the first one always start with the N terminus. Okay, so if you look at the structure here, so we give the amino acid number 1 glycine. Can you see that the glycine? So with the N terminus, can you see that NH3 is with the ions, right? It can form with the ions. So therefore NH3 here. So we continue all the way toward the last one, glutamic acid, which is COO minus or COH, which is the carboxyl N. So we have the N terminus and also the C terminus. Okay. So what type of question asked? I mean, for this part, first, we need to know what is the definitions of the primary structure. Second, we need to do a calculation. Okay, so what are the calculations that we need to calculate here? So what type of calculation question? Okay, I will show you with the number first. Later, you come out with the formula. Okay, so first, how many polypeptides can be formed? Okay, theoretically, theoretically. Okay, so let's say first, you are given, okay, 6 amino acid. Okay, 6 different types lah. Let's say A, B, C, D, E, and F. Okay, you have 6 different type of amino acids, and then you have to use 6 amino acids, six different type of amino acid to build a polypeptide. Okay, to make a polypeptide with, let's say, 10 amino acid residue. Now, what's mean this 10 amino acid residue? So means that this polypeptide, the length is 10 amino acids. Are you clear? The length of this polypeptide, 10 amino acids. So if I give you A, B, C, D, E, F amino acids, how many polypeptide we can form? Okay, so question is asked this way, then automatically, logical thinking, you should know that if I have 10 amino acid long, and I only have 6 choices of amino acid, so means that I have to repeat to use, right? If I don't repeat, the maximum length only 6 amino acids, correct or not? Are you clear? If I only have 6 amino acids, I want to make a polypeptide with 10 amino acid the long, definitely I have to repeat. Okay, so means that how to solve this kind of question, you have to, you have learned this before in mathematics. Well, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 positions. So at the first part, at the first amino acid, we can put A, we can put B, C, D, E, or F. So I have 6 choices, correct or not? Okay, but because we can repeat the second slot, also 6 choices, and you continue, so the number of polypeptides theoretically that can be formed will equal to 6 to the power of 10. Are you clear? 10 times, correct or not? 10 slot, each slot you have 6 different types of amino acid, the choices that we can put in. So the answer will be 6 to the power of 10. But again, as I say that this is on paper calculations, it doesn't mean that we're going to get this number, but this is the maximum number that we can get. Are you clear? Okay, so you can have a look. This one, I stop recording. Okay, let us look at second example. Okay, so you are given, okay, 10 amino acid or 10 types of amino acid. Okay, 10 amino acids. So now we want to make, okay, to make polypeptide with, okay, 6 amino acid residue. Are you clear? So these are questions, then you'll be curious, right? Need to repeat or cannot repeat, because I have more choices than what I need. Correct or not? Okay, so it depends on the question. So if repeat is allowed, and B, repeat is not allowed. So how you solve this question? So look at A. If repeat is allowed, so I have 6 amino acid residues. So 1, 2, 3, 4, 5, 6 slots, right? So at each time I have 10 choices and I can repeat. So therefore, first time I have 10 choices to put in, second time also have 10 and so on. So therefore, number of polypeptides formed or can be formed will equal to 10 to the power of 6. Cannot 10, 6 slots, each slot you have 10 choices. But if repeat is not, okay, when the repeat is not allowed, so I have 6 slots, 1, 2, 3, 4, 5, 6. First time I will have 10 choices, but when I use the first one already, I have 9, 8. Okay, each time I have less and less choices. Correct or not? Okay, so in this case, number, okay, you learn about this in the permutations, okay, in mathematics. So number of polypeptides that can be formed will equal to take 10, from the 10 choices, you choose 6, okay, to arrange. So it's with 10p6, permutation take place. Now, why permutation, not combination? Because you need to arrange them. Like I say that amino acid A, B, C, and B, C, A will be different. Are you clear? Clear? So this is the second example of the calculation. Okay, let us try the questions. Okay, so you are given n types, okay, of the amino acid to form a polypeptide with R amino acid residues. So means that you have R places, okay, 1, 2, 3, 4, okay, R types, okay, R times, okay. So each time you have n choices to put in, correct or not? Okay, so means that number of polypeptides that, okay, can be formed equal to n to the power of R, okay, n to the power of R. Okay, do I need to ask whether I need to repeat or not? Definitely have to repeat because n is less than R. Number of choices that I have less than the what we want. So we have to repeat, no choice, right? Okay, now next. So you're given the n type of amino acid to form polypeptides again, okay, with R amino acid residues. So given that R now less than n, so means that what we have more choices than the needed one. R is the needed one, required one, n is the total number of choices. So if no repetition is allowed, okay, if we don't want to repeat, okay, so no repetition, so that's why I mean no repetition. Okay, so B1. So means that every time you're going to have less and less, correct or not? Okay, we cannot repeat. So means that first time I have 10, second time I have 9. So this one, number of polypeptides, okay, that can be formed will equal to, I have n choices of the amino acid, I choose R number to, okay, I choose R number to arrange them. Okay, so NPR. Very good. Okay. Now third, not third, the second part. Okay, repetition of amino acid is allowed. Same thing. If repetition can allowed in this case, so I need to have R amino acid residue. So each time I have N, I can put in, right? So therefore, number of polypeptides that can be formed will equal to n to the power of R. It depends, R is the number of slots. So how many slots that we do have here? Okay, so that will be the concludes for the primary structures. Okay, so now we continue with the secondary structure. So secondary structures, then we focus on how these amino acids, the polypeptides coil into the alpha helix or fold into the beta pleated sheets. Okay, so how it look like? If you look at this, alpha helix is very nice, okay, a spiral shape. Okay, they have their own very fixed kinds of the helical structures. Okay, can you see that? And also beta pleated sheet, can you see that? It's something like a piece of paper, and then you fold it like this. Okay, so the bonds that actually maintains the alpha helix or beta pleated sheet is hydrogen bond. Are you clear? Hydrogen bonds maintain this alpha helix and beta pleated sheets, but always very careful. The hydrogen bonds that form are within polypeptide backbone. Right now, okay, within the polypeptide backbone, where is the R group? In this case, when you study the secondary structure, R group is not involved. Are you clear? So R group is not involved. We don't involve R group yet at the secondary structure. Okay? When you study secondary structure, we ignore the R group effect. Okay, so therefore we're going to study what? We're going to study how or this the polypeptide when it coil into this, okay, alpha helix or beta pleated sheet. Okay, and how these hydrogen bonds can be formed. So if you look at this during the formation of the peptide bond, when you look at the formation of peptide bonds, okay, you have this central carbon C, N, okay, and continue C, N, and then you have the C. Okay, let me do something. C, N, and C, N, for example. Okay, and you can see that C here we have C double bond O H. Clear or not? Okay, and then C double bond O H, and this C was C double bond O. Oops, sorry. This one, C double bond O and H, for example. And we do know that, okay, can you see that? O is delta negative, H is delta positive. So therefore, they can form the hydrogen bond. Can you see that? Hydrogen bonds can be formed between the NH and CO. So these are involved. Can you see that? CCN, this one, can I say CCN? This one we term it as polypeptide backbone. So where is the R group? You look at this, R group actually here, but R group does not involve. Can you see that? All R group, they do not involve in the formations of the hydrogen bonds in secondary structure. Do you realize it? Okay, so the formations of the hydrogen bonds to form this alpha helix and beta pleated sheet only involve the oxygen atom of the C double bond O and H atom, okay, of the NH group here within the polypeptide backbones, and R groups, can you see that? R group, they are projected sideways, therefore they are not involved in the formation of the hydrogen bonds in alpha helix or beta pleated sheets. Can you see that? Beta pleated sheet, also the same thing, C double bond O and H from hydrogen bond, H and O hydrogen bond. So this hydrogen bond maintains the alpha helix or beta pleated sheets here. Okay, so now we zoom into more precise, okay, particularly alpha helix. So you look at the alpha helix, how this alpha helix actually is formed. So in alpha helix, this hydrogen bond formed between the oxygen atom, can you see that, of C double bond O group of one amino acid, and the hydrogen atom of NH group of amino acid 4 places ahead of it. So if this is amino acid number 1, then hydrogen bond will be formed between amino acid number 1 and amino acid number 5. Can you see that? Number 1, so 4 amino acid ahead, 1, 2, 3, 4. Then yes, number 2, then with number 6. If number 3 with number 7. So means that you're going to form a very, very precise turn every time for amino acid. So if I put it in this structure, can you see that amino acid number 1 and amino acid number 5, when you fold it, they always together. Can you see that? Number 2 and number 6 always together. Number 3 and number 7 always together. Number 4 and number 8 always together. So therefore, hydrogen bonds can be formed. It's something like you place the blocks. Okay, so this is the first block. Okay, then you place the second block. Okay, then you place the third block. Okay, then the fourth blocks, you put it here. Okay, you try to imagine, imagine this amino acid as a block. So it means that how we join them? We join them by the peptide bonds, right? Peptide bond join them together, peptide bond join them together. So when you come to this is number 1, this amino acid number 2, amino acid number 3, this amino acid number 4, right? So how about amino acid number 5? Amino acid number 5 will be here. Can I see that? So how we join them? We join them by the peptide bond. Can I see that? So amino acid number 6. So we form this helical structure to amino acid number 6 will be here. Can I see that? So peptide bond. So how they link? So how they link? So they link number 1. Okay, again, sorry. Number 1, number 2, number 3, number 4. This is number 5. So number 1 and number 5, 4 amino acid ahead. Can you see that? So 1, 2, 3, 4. 4 amino acid ahead. So then they form the hydrogen bond. Can you see that? They form hydrogen bond. So number 2 and number 6 form hydrogen bond. Number 3 later, okay, if I draw it out, so now we have another block here. So a peptide bond join. Can I see that? Okay, so then the hydrogen bonds. Can you imagine that? So you make a helical structure. Are you clear? So turn helix. Can you see that? Go to the helix like this. So this is how the alpha helix actually form. Can you see that? So where is the R group? Okay, R group projected sideways. R group, R group, R group projected sideways. R group, R group. So therefore, they don't involve. Can you see that? R group, they don't involve in the formations of the hydrogen bond. So it's something like cylinder. R group actually projected sideways. Okay, so you can see that. Where's R group? R group will be here, projected sideways. Okay, R group, R groups, R group, R groups. Okay, so this is how alpha helix actually they are formed. Okay, so you can see that's alpha helix, alpha helix. So R group projected sideways, but the R group later can interact. Okay, R group they can interact later. Okay, so how about beta platelet sheet? Beta platelet sheet is a second form of the regular secondary structure. So this beta sheet consists of beta strands that connect laterally. Okay, at least 2 to 3 backbones. Okay, by hydrogen bonds. So you can see that in this diagram. So can you see that? There's one strand, make a turn, second strand. Okay, can I see that? One go in this case and then come like this. So this is called as the beta platelet sheet. So imagine that you cut a piece of paper, cut another piece, okay, a strip, and then you place them laterally. Okay, when you place them laterally, then can I see that the H and the O and the H, they can form the hydrogen bonds, and the R group, they are not involved in the formations of the hydrogen bond within the carbon or within this polypeptides backbone. Can I see that? NCC or CCN, 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 CCN. So they won't form the hydrogen bonds. Are you clear? The R groups, okay, within R group, but they form the hydrogen bond within this polypeptide backbone. Okay, so in both alpha helix and beta platelet sheets, hydrogen bonds are formed between the polypeptide backbone, okay, of this amino group with the H atom. Carbonyl group is O. C double bond O is a carbonyl group. Okay, so the R group are not involved in the formation of the hydrogen bond. So hydrogen bonds, okay, can be broken down by the high temperature. Okay, so this one you need to know. Okay, so we do know that for proteins, okay, to functions, they must be able, okay, the polypeptide must be able to fold into a very precise three-dimensional shape. So these three-dimensional shapes, okay, so we term them as the tertiary structure. So we're going to look at it, how they fold and who maintain this shape. Can you see that this kind of shape? For example, after they fold, you can see that this is something that we can put in our enzyme. If this is enzyme, we can put this, maybe the active sites for the enzymes, correct or not? Okay, so we're going to look at how this precise three-dimensional shape can be maintained and what are the elements or criteria that we're going to study at the tertiary structure. So as I say that the shape is very precise, and how in exact shape by highlights here interaction between the R group. So now we only go into the interactions of the R group. So how R group interactions can make these polypeptides fold in a very, very precise shape. So it means that today I fold it, tomorrow I fold it, and 10 years after that I fold it, it's still the same shape, okay? Because a very precise interaction between the R group of the amino acids at the different parts of the chain. So how this interaction actually take place? If you look at the polar R group, okay, so that's why we learn in amino acid how to differentiate between the polar R group, between the charged R group, between the non-polar R group or hydrophobic R group, because we need to learn them now. Because between the polar R group, particularly where you look at this OH, NH, okay, so we do know that O and N, they are delta negative, H, they are delta positive. They can form hydrogen bonds, okay? And cysteine, okay, cysteine very special. Cysteines, if we look at amino acid R group or the cysteine, you can see that they have SH. Okay, if another cysteine, they have a sulfur SH. So oxidation process can take place by removing the hydrogen atom, make a covalent bond join two cysteines together, right, to interact with it here. So this one becomes two sulfur here. So this bond between two sulfur, so this bond is called as a disulfide bond. It's the strongest bond among all the interaction because it's a covalent bond. Are you clear? It's a covalent bond that link the two cysteine amino acid together. Okay, and then you have ionic bond between the amines and also the carboxyl, because amines will be positively charged right down, carboxyl groups will be negatively charged, COO minus. So therefore, one positive, one negative, they have this electrostatic charge. Okay, so this before this we have delta negative, delta positive, also electrostatic charge, but it's a brief one. It's not a completely charged. If you compare to the ionic bonds here, because they're completely charged, positive and negative, so therefore you can see that between these two they form the ionic bond. And then between the non-polar R group, they're clustered together because, okay, try to imagine I'm weak, I don't like water, you don't like water, then we cluster together. Okay, so when they cluster together, then they form these hydrophobic interactions. Okay, we term that hydrophobic interaction. Basically, I don't like water, you don't like water, then we put all this R group together, and this R group actually interact. Okay, can you see that? It's not interact. This R group, they how to say that? They protect each other by forming these hydrophobic interactions. So in terms of the ranking, which one is the strongest? Okay, strongest to weakest, you arrange them. So first one is the covalent bond, disulfide. Okay, disulfide is the we call this the strongest bond here, followed by second. Okay, so the second ones will be these ionic bond, and third hydrogen right now bond, and number 4 hydrophobic interactions. Okay, so in this case, disulfide bond, because it's covalent bond. Covalent bond is the strongest bonds. It's the strongest bond compared to the ionics. Okay, so ionic bonds can be broken down. So how to break down disulfide? You want to break down disulfide bonds, then we need to use a reducing agent, chemical. Ionic bond, we can use a change of the pH. We can increase the pH or decrease the pH. We can actually break the ionic bond, hydrogen bonds. You increase the temperature, you provide the heat energy, you can break the hydrogen bond. With change pH also sometimes can break the hydrogen bond. Hydrophobic interaction, actually a slight increase of the temperature, you will be able to break the hydrogen, this hydrophobic interaction already. So disulfide bond actually is the strongest bonds among all of these interactions. Okay, so what you need to do now, okay, try to figure out, okay, we have 4. 1, 2, 3, 4 interactions here. So name those or label those interactions now. Okay, so how we label? Can you see that, guys? CH3, CH3. So that's why you need to know how to differentiate the R group. So CH3, CH3. Can you see that this kind? So this one is the hydrophobic interaction. Okay, because they are they don't like water, so we put them together. Okay, then you look at this. OH, O delta negative, H delta positive, and whenever you draw the hydrogen bond, it must be a dotted lines. Okay, this one's the hydrogen bond. Okay, so between this sulfur and sulfur, so 2 sulfurs, so disulfide. Now be careful how you spell. Okay, it's not pH, it's disulfide. And the last one positive, 1 negative, definitely this is the ionic bond. Okay, so write down disulfide is the strongest bond. So to break this, we need reducing agent. Okay, we need reducing agent to break this disulfide bond. Okay, so ionic bond, we term that as a weak bond. Okay, weak interactions. To break these ionic bonds, we need to change pH, or pH change. Then can break this ionic bond. Hydrogen bond again is a weak bond, but if you compare this ionic bond still stronger compared to hydrogen bonds. This one actually we increase the temperature. Not the change only, but increase temperature. We can break the hydrogen bonds. Actually, when you change pH, you can break the hydrogen bond as well. Okay, 2. But when you talk about temperature, increased temperature only can break hydrogen bonds. Okay, and also hydrophobic interactions right now is the weakest. So increasing temperature, a slight increase in temperature, you can actually break the hydrophobic interactions already. Can you see that? So that's why covalent compound, they are linked with this interaction, a very weak interaction. So that's why increased temperature, you can melt, right? You can melt, okay? Or you can actually make it into gaseous form already. So that's why covalent compound, most of them, okay, they are the interactions are very, very weak. So that's why they exist as the diatomic gas. Okay. So the last one we're going to look at it here is the quaternary structure before we take a break. Okay. So when talking about quaternary structure, we're going to look at it how these 2 or more than 2 polypeptide chains are held together to form a quaternary structure. For example, quaternary protein including the hemoglobins and also collagen. These 2 we're going to learn it later when we look at how these 4 polypeptide chains actually combine together to form a complete protein, okay, or collagens molecules, okay, and we're going to use them as a model to study globular protein and also the fibrous protein. And quaternary structure, we don't only study how many polypeptide join together and how they join together. So we are going to look at it against interactions of R groups. Okay, which link, okay, the interaction of R group which links, okay, a polypeptide chain together. For example, if a collagen, you can see that if collagen, this is 1 polypeptide, 2 polypeptides and 3 polypeptides. So we have 3 polypeptide chain. How they actually link together, how they actually interact with each other. So by hydrogen bonds, okay, by hydrogen bonds, okay. Or for example, you may have the disulfide, you may have hydrogen bonds, you may have the hydrophobic interaction that make these polypeptide actually join together to form a complete proteins, okay. So I summarize here, primary structure, okay, we only look at type of amino acid and the sequence of an amino acid that form the polypeptide chain. Okay, then we finish analyze the primary structure. We continue to the secondary structure. We look at the alpha helix and beta plated sheets. Whether how many alpha helix, how many beta plated sheets, how they coil, how they fold. Those are the secondary structure. So secondary structure, we look at the alpha helix, beta plated sheets, and we look at the hydrogen bond formed between the oxygen atoms of the C double bond O group and hydrogen atom of the NH group. Or not. Okay, within, and this C double bond O and NH within the polypeptide chain or polypeptide backbone where the R group is not involved in the secondary structure. Okay, quaternary structure, we look at how this protein fold into the precise, a polypeptide fold into precise 3-dimensional shape, where we're going to look at this, how the R group interaction. So we have 4 kinds of R group interaction between the 2 cysteine, the sulfur. Then we look at this, a sulfur atom. Therefore, we look at this disulfide bond. Then between the positively charged R group and negatively charged R group, then we're going to get the ionic bonds. So between 2 polar R group, we get the hydrogen bond. Okay, between 2 hydrophobic R groups, then we get the hydrophobic interactions. And we need to know how we can break this bond. Okay, for example, disulfide, we need to use the reducing agents to break the bond, disulfide. And we want to break the ionic bonds, we change the pH. Increase the pH or decrease the pH, we will be able to break the ionic bond. But if you want to break the hydrogen bonds, we can use the heat energy. So how to supply the heat energy? We actually supply the heat, right, by increasing the temperature. And hydrophobic interaction is the weakest one. And then we come to the quaternary structure. Then in the quaternary structure, we look at how many polypeptides actually joins together to form a complete protein and how these polypeptides can interact with each other through the R group interaction that we learn in the tertiary structures. Okay, so with this, I have done for the polypeptides.